Okay, welcome to Guidesheet number 4 on electric field strength. The electric field strength E is a vector quantity. It's defined as the force per unit charge on a small test charge. So to find it, we take the force, electrical force, and divide it by the small test charge that is in the field, not the charge that creates the field. Since we are talking about force per charge, the units are going to be force, newtons, per coulomb, or Newton Coulomb minus 1. So it tells us how much force per charge, not just the amount of force. The electric field vector direction is defined as the direction a positive test charge would move. So the field is always out from a positive isolated point charge and into a negative isolated point charge. So if you're not sure, just put a little dot, call that a positive charge, and think about which way it would go if you were to let it go. If it gets pulled in toward the charge, then the field line, the electric field would go in, and if it gets pushed out, then the electric field line would go out. Okay, so we're just going to use force over charge to calculate the electric field strength here. Here it's going to be force 0.05 newtons divided by charge, positive 1.6 times 10 to the minus 6 coulombs, which is going to give us 50,000 newtons per coulomb. In the second one, we have doubled the amount of force that the same charge would feel, so we get 100,000 newtons per coulomb of electric field strength. So notice those numbers are relatively large. It is per coulomb. It's hard to get a coulomb of charge in one place, so we get a large number because we typically have small charges moving around. Number 5, the object with a charge of 2 times 10 to the negative 4 coulombs creates an electric field. The test charge of 1.0 times 10 to the minus 6 coulombs feels a force of 0.05 newtons. Now, the key there is you don't want to use the charge that creates the field. You want to use the test charge. So the test charge is just force 0.05 divided by charge 1 times 10 to the minus 6, and we're back to 50,000 newtons per coulomb as we were in number 3. Again, number 6, an object creates the field. We don't care about that one for the field strength measurement in this method. We just want to take the the force 0.1, and we want to divide that by the charge, which is 2 times 10 to the negative 6. And we've doubled the force, but we've also doubled the charge, so we're compared to number 3, so we're back to 50,000 newtons per coulomb. This one, again, it's not about the charge that creates the field, it's about the test charge. So it's 0.1 newtons, and it's 1 times 10 to the minus 6 coulombs. We've been there before. That is the same values in number 4, so we're back to 100,000 newtons per coulomb. Okay, so here's our picture of testing. So big Q is creating the field here, and then little q is over here. That's our test charge. So this is what we're testing the field with. This is the thing that sets up the field. Now if you were to look at that field, it would move outward radially in all directions from the positive charge. Okay, so A, if the charge of the test charge Q is doubled, then it will experience. So if we doubled the test charge, it's force per charge, so twice as much charge tells us that we will have twice as much force. The electric field strength itself would be the same. We haven't changed the field, we've increased what's in the field. So that's like having a heavier object here on the Earth the object has more weight because it has more mass. We didn't change the Earth at all in that calculation. B, if the charge Q is doubled, then the test charge will experience. Now, if we double the test charge, Coulomb's law tells us that doubling one of the charges will double the overall amount of force. And in this time, the electric field strength, we didn't double the test charge, we doubled the charge that was creating the charge. And finding the charge from the actual charge that creates it, electric field, sorry, from the charge that creates it, it would be E equals KQ over R squared. So if we doubled the Q, we're going to double the field strength as well. Okay, now distance, again, it's going to be based on Coulomb's law. So if we double the distance between the charge and the test charge, then we're going to get less force, and it's going to be less by the square. So that means we're going to be 1/4 of what we were before. 1/2 squared is 1/4. And then the electric field strength, again, is also based off of R squared, so it's also going to be 1/4 as much. So the correct answer would be 1/4 as much. So changing the test charge does nothing to the field, as in A. Changing the charge on the field is going to make the field either stronger or weaker, depending on if you add or subtract charge. And then changing the distance, closer you are, the more force you're going to have, the larger the E field is going to be, just like G is larger closer to a planet like the Earth, little g, the local gravitational field strength, than it is when you're farther from the Earth. Alright, so we're going to try a couple of those situations. A fly accumulates 3 × 10⁻⁻⁰ coulombs of positive charge that flies through the air. What's the magnitude and direction of the electric field location 2 centimeters from the fly? If we assume the charge on the fly is a small point charge, we're looking at a distance 2 centimeters away. Since we know the Q, the charge that creates the field, if I call that capital Q, then the electric field at some distance is going to be K, the electric field constant, which is 9 × 10⁹ Q over R squared. So 9 × 10⁹ multiplied by the charge, 3.0 × 10⁻⁻⁰. That needs to be in coulombs. And then the distance needs to, so 2 centimeters, we're going to divide that by 100 for centi, and we get 0.02 meters. So the electric field strength is going to be divided by 0.02, that's meters, and we have to square that. Okay, now that gives us a value of 6,742. We really only have two significant figures, so 6,700 newtons per coulomb. And then in terms of direction, depending on how you draw it, it's always going to be, if in my case I drew it, it's going to be to the right. But you can say that because it is a positive charge creating the field, then it will always be outward, away from the field, away from the center charge that creates the field. Okay, then we have Gordon, the night custodian, dusting off a classroom globe with a feather duster, causing the globe to acquire a charge of -8 × 10⁻⁹ coulombs. So that's the charge that's creating the field. We want the magnitude and direction of the field at a point 0.4 meters from that, from the center of that charged globe. So we have that in meters, so we don't need to change that. Again, we have a distance and we have the charge that creates the field, so the electric field strength now will be KQ over R squared. Again, that's 9 × 10⁹. That's in newtons, coulombs, and meters, so we need to be in base units with the others. -8.0 × 10⁻⁹ coulombs. And we're going to divide that by the distance squared, 0.4 meters. Just don't forget to square it. Okay, so alpha K, we have a negative. It's going to give us a negative answer, which in this case indicates the direction of the field. So we get 400 And 49.5, which is going to round the two significant figures of 450. That's again newtons per coulomb of charge. And then this time it's going to be inward. Really the answer is negative, which indicates it's a negative charge setting up the field, and the electric field is always in toward negative charges. Okay, so that's the basics of electric field strength, how you calculate it for various situations and the direction of that field.